Morning, everyone. This is going to be the second video now on an introduction to real analysis. These are roughly what you talk about in week 2 or topic 2 of your 517 class. So we're going to start with the idea of a function, which thinking of it as these abstract sets A and B, and it's just this mapping of items in A into items on B. Then start to classify these mappings, these functions, by looking at the domain, the set of things from A that are mapped, the value of a particular entry of A, so f of A equals some little b, which is a member of the set B, the range, which is the set that you're mapping into, that gets associated with things from A, the complete set of that. So the range being a subset then of the codomain, the codomain being B, and then the range is the items out of B that get mapped into. The image of a particular subset is the subset of the range for that set in A. So you can have the image of a subset of A in B, which then would be a subset of the domain, of the range. And then, onto, meaning that it maps onto everything in B, has something that's mapped onto it. When it can be, if it's the inverse image of something, so the set of items that get mapped to a particular item or subset of B, it's kind of doing the same thing as the image, just going the other way. And then the idea of a one-to-one mapping, where every unique item gets sent to a unique item in the other set. We already talked about the idea of an equivalence relation, and then we start to, again, classify these as being finite sets, infinite sets, or countable, meaning you can establish a one-to-one association with the positive integers or natural numbers. And then uncountable sets are things that cannot be counted, and then at the concept of at most countable. We then really go into this, analysis of sequences. And sequences become one of the approaches to ultimately continuity, which is probably about as far as I'm going to go with this preview. So you could think of a sequence as being a function from the natural numbers to a set of real numbers, let's say. That would be a real sequence. So there's a first number in your sequence, there's a second number in the sequence, so we're mapping the natural numbers through the indexing process to this sequence of numbers in the real numbers. And you can kind of start this indexing wherever you want, and I tried to show you the notation here, starting at n equals 0 or starting at n equals m. But if you usually leave that off, you just assume that the sequence is starting at 1. So you're indexing them 1, 2, 3, 4, 5, what have you. And you could then define a sequence of elements of any set. It's just a matter of the first item of that set, the second item of that set, the third item. You're giving this kind of association between the natural numbers then and the elements of a set that there's nothing special about this being real numbers. All right, and so one of the things then you start to look at is what kind of properties get inherited from, the other set of numbers. So if we just kind of stick to real number sequences for most of the rest of this discussion, if you have an infinite subset of a countable set, so that countable sets could be finite or they could be infinite. But if you have an infinite set that's countable, for example, the rational numbers, then you take an infinite subset of that countable set, and it must also be countable. By the way, the proofs that are on here, the numbering, and you're going to see this more and more as we jump through these, is referring to proof numbers in your book, which is the Baby Rudin. You can probably find a copy of it online if you wanted to learn more about some of these things. We'll also use the concepts of union and intersection of the sets that you're indexing to talk about things like sums and products of the sequences. Again, an infinite sequence of a countable set is countable, and then a corollary of that is the proof that we already talked about, I think, in week 1 here, about the set of all rational numbers actually being countable. We go on to define a metric space. I think this is important. This is yet again one of those structures such as fields and rings and so forth. So a metric space now, you have this mapping or this binary operation, we'll call it D, which takes two items from your set and gives you back a real number. And it has to satisfy these three properties that for any unique items in M, so if P does not equal Q, then the D stands for distance. The distance from P to Q, or the metric value associated to these two, is always going to be positive. And if the P equals Q, in other words, you apply this binary operation to the same element from M twice, dpp is always going to be 0. Number 2 is then that it's symmetric. The distance from P to Q is the same as the distance from Q to P. And the third one is your basic triangle inequality. And this is extremely important because this triangle inequality is going to be used over and over and over again in a wide variety of contexts in an analysis course. The distance from P to Q plus the distance from Q to R is bigger than or equal to the distance from P to R. You could think of it like the sum of the lengths of two sides of a right triangle is always going to be greater than or equal to the length of the hypotenuse. And it's really only equal in the case where they're parallel. But that's enough to define a metric on a space. And so there's a couple of questions on here, and you can try these yourself. I'm not going to give you the answers. Is this one going to be a metric? And the second one. We get into point set topology. Now, I'm just listing these definitions on here as part of this preview. I'm not going to go into all of them, but we define what it means then for an interval of real numbers and segments that are open, closed, or half open. We distinguish between open and closed balls, being the set of all numbers that are a certain distance using your metric in your metric space away from a fixed point, usually the origin. K-cells, convex subsets, and then neighborhood, the neighborhood of a point, a limit point for a set, an isolated point, a closed set, not just a closed interval, meaning that it contains all of its limit points, an interior point, open set, complement, a perfect set, what it means to be bounded, and what it means for a set to be dense. We go over some definitions about the supremum of a bounded above non-empty set, and so forth. And this is really where I almost want to end this. We're going to talk about the concept of compact sets. Compact set is an open cover. You start with the concept of an open cover, the union of a countable collection of open sets. It could be an infinite collection, but it's a countable collection of open sets. And then you can say that a set or a subset of this space is compact if every open cover for that subset contains a finite subcover. So the real numbers, for example, are not compact because I can take an interval like from 0 to 1, and I can take the open interval from 0 to 1, open on both sides, and I can create a sequence of sets that are from 0 to 1 minus like a 1 over n piece on either side. And so when I iterate that infinitely, I'll eventually cover all of the points in that set. But if I leave any one of them out, create a finite subcover so it stops at some point, then there's always going to be something missing. So I can demonstrate an open cover of the open interval from 0 to 1 that doesn't have a finite subcover. So an open interval from 0 to 1, for example, is not a compact set. And so this idea of sets being compact becomes very important. It's kind of a weird definition at first, and it's important that you start to think about this idea and some of the big theorems that come about because of it. Compact subsets of metric spaces have to be closed. Closed subsets of a compact set has to be compact. But if you leave one of these things out, it doesn't necessarily work. Like closed subsets of a metric space are not necessarily compact. So it's that set that you're a closed subset of had to be compact itself in order for that closed subset to inherit the compactness from that piece. K cells are compact. And then we get to the Weierstrass theorem. Every bounded infinite subset of Rk has a limit point in Rk. We talk about the Cantor set, which is where you remove the middle third, you get this kind of a highly fractured set, but it ultimately is the counterexample to a lot of other theorems, this idea of the Cantor set. And finally, that's really the end of the chapter 2, which is topic 2 in our analysis class. There's some additional slides I left in here from the previous class, but we'll go over some of those in the next video because they're now in chapter 3 as opposed to chapter 2 of this sequence of introduction to analysis videos. All right, I'll see you next time.